The Ukrainian AI community used to create, develop, and educate for a shining future. But then Russia ruined our peace. We switched to a new reality. We do our best to defend our country. The brightest AI minds came to share knowledge with us. Together, we will build a technological and secure future. Peace in Ukraine equals peace in the world. Support Ukraine. Support the AI community.
Hello, hello. Welcome all. Welcome at AI for Ukraine. This is the series of workshops and lectures held by international AI experts to support the development of Ukraine's tech community during the war. So thank you for your support. Thank you for donations. Currently, we collected almost 300,000 of Ukrainian hryvnias, and almost all of them will go to the Ukrainian foundation, the biggest Ukrainian foundation known Come Back Alive. So my name is Daria, and I'm a data engineer currently working at Alex, Ukrainian company. And how am I related? I'm gonna be your moderator for this lecture today. So the topic of our lecture today is unveiling transformers with Lego. Our star lecturer is Sebastien Bubeck. So welcome here in a couple of moments, but meanwhile, I would like to show you the tool we're going to use today for questions. The tool is slido.com, so please open it in your browser. You can find link also down under the video in description field. So please open it in browser. You should actually put AI for Ukraine code, name and mail, and then you will be able to ask questions. So let us test together. I will start the simple poll with a question, and we'll gather your answers for a few moments. So let us know, please. Are you using transformers for your work now, or so? So while you're answering, I invite Sebastien here in a moment and say a couple words about him if you don't know him. So he leads the Machine Learning Foundations group at Microsoft Research Redmond. He joined Microsoft at 12-14 after the 3 years as an assistant professor at Princeton University. He received several Best Paper awards at machine learning conferences for his works. He also wrote 2 monographs. The topics analysis of statistics and stochastic and non-stochastic problems and convex optimizations. So I see Paul is currently working. Maybe you see the results on the screen also. Yeah, Sebastien is here. Sebastien, welcome.
Thank you.
I see about 38% of people actually work and use transformers for his work. So you're going to deal with professionals.
That's great.
Expect a lot of questions. So I'll pass you the word in a couple of moments, please. And I'll come back here for a Q&A session, as you understand. And I must ask you, please upvote the most liked for you questions. We definitely will answer them because they will be rated and placed higher in the list. So, and again, thank you for donations. You can also donate during the live stream. The link is under the video in description. So please, Sebastien, welcome again. I'm giving the word to you.
Great. Thanks a lot, Daria. So I'm excited to be here for this cause of AI for Ukraine. So I will be telling you about unveiling transformers with Lego, which is joint work that I have done with my team here at Microsoft Research. So the first author is Yi Zheng, who is our postdoc, who is really fantastic. And other collaborators include Arthur Backers, Ronan Eldan, Surya Gunasekar, and Tal Wagner. So I think the first thing I want to do in this lecture is to tell you about the words in the title. So, transformers and Lego. So that's what we're going to start with. So let's start, with transformers. So what are transformers? So if you go online on the internet and you search for transformers, this is, I think what you will see. You will see this picture, this diagram. Now, honestly, good luck to understand anything about transformers just by seeing this. So, of course, transformers are a certain type of neural networks, as I will explain. But to me, this diagram is not enough at all to explain what are the computations being done inside the transformer. Now, actually, it turns out that transformers are extremely simple objects mathematically. So I will be able to explain to you in just a few minutes, everything you need to know about them, about their operation. And then I will tell you about this Lego task, which is a synthetic reasoning task that we came up with to kind of understand the dynamic of learning with transformers. But that will be in the second part. Let's first spend, a few minutes on transformers. Okay, so what are they? So the key distinguishing feature for me between transformers and neural networks that came before, like convolutional neural network, maybe you've heard of ResNet, things like that. The key difference is that transformers, instead of processing a single high-dimensional vector, they process a set of high-dimensional vector. So instead, like convolutional neural network, they process images one by one. Here, transformers, what they will do is that they will get a set. For example, an image will be represented as a set of patches. That's one example. Okay. Now let's explain, how this set mapping is being done exactly. So transformers are neural network which are multi-layered. Now I will tell you what each layer is doing. So a layer takes as input, a set x1 through xn. So it has n elements in this set. Each of those elements are elements of r to the d. Okay, so you have n high-dimensional vector in dimension d. Now, one layer of the transformer will process this and give you from x1 through xn, x1 prime to xn prime. Now, I just need to tell you what is the formula to go from x1n to xn to x1 prime to xn prime. Okay, so that's what I'm going to do now. So the way this mapping is done is by alternating two operations. One is the so-called multi-head self-attention, which I will explain to you in a second. And then once you have done this multi-head self-attention, which is really a set operation, this is going to be followed by a simple feed-forward neural network, which I won't be explaining, what is a feed-forward neural network. I assume that you guys know about it. So this feed-forward neural network will just be applied token-wise. So once the self-attention has mapped x1 through xn to x1 prime to xn prime, then each one of those x1 prime, etc., is being processed by a single feed-forward neural network. Okay, and in addition to this self-attention and feed-forward, there are also residual connections and layer normalization. These are much less important for the discussion today, so I will just ignore them. But these are very, very simple operations. Residual connection is just adding a little bit of your input, and layer normalization is just making sure that everything is normalized in L2. Okay, so all I need to do, I think at this point, is to tell you what is multi-head self-attention. And I will start by telling you what is a single head self-attention, and moreover, an unparameterized version of single head. So let's go through this formula. So what you do is that you have one of those xi's, which we refer to as tokens. So I'm going to call x1 is a token, x2 is a token, etc. So you have a list of tokens. Now I'm going to tell you how single head self-attention processes a single token xi to produce a new token xi prime. And the way it's going to do it is as follows. What I'm going to define is a probability distribution, P sub I. This probability distribution is over the other tokens. And the semantic of it is how much attention token I is giving to other token. So Pij is how much attention token I is given to token j. And the way we're going to decide how much attention token I is given to token j is very simple. We're going to compute a score, which is nothing but the inner product between the token xi and the token xj. So if the token xi and the token xj are very much aligned, then we give them a high score. If they are close to each other, then we give them a high score. Okay. Now those scores, they can be negative, like an inner product can be a negative quantity, and we want a probability distribution. So the first thing we do is that we, make this inner product, this score, go through an exponential. Okay. okay? So that we have non-negative numbers, and then we normalize by this capital Zi so that it sums up to 1. So this is a formula for how much attention token I gives to token J. And now the transformation is that token I, so Xi, is simply going to be replaced by a weighted combination of all the other tokens, where the weights are given by the attention that this token is given to the other tokens. So Xi just becomes the sum of Pij Xj from j equals 1 to n. This is a single head self-attention. Now, what transformer will do, you understand that this is a completely unparameterized transformation. And of course, in our network learning, we want to have lots of parameters, which we're going to update with gradient descent, and we're going to learn like that, etc. So I need to tell you how we're going to parameterize this thing. Now, a parameterized self-attention, it's exactly the same formula, except that you add a linear transformation, a linear operator at every place in this formula where you see a token. So notice that there are 3 places where you see a token. You see a token here, xj. You see a token here, xi, and you see a token here, xj. Okay, sorry, I think you can't see my mouse, but in the weighted combination, you see a token, and in the inner product of the score, you see 2 tokens. Now, what the 3 linear operations are going to be the query, the key, and value. So the linear operation that you put in the xi for the score is called the query. You think about the token xi as a query. The linear operation that you put on the xj in the score, this is going to be called the key. You look at a token as a key. So you look at how well the query matches the different key. So these are the 2 linear operations that you put in the exponential. And then in the weighted combination, the xj's that appear in the weighted combination, these are the value. And you add a distinct third operation there. Okay. Now, multi-head self-attention, it's simply going to be the same thing, except that we do it in parallel, and that the linear operation, instead of being mapping from dimension d to dimension d, they are going to be mapping from dimension d to dimension d over h. So you have some kind of dimension reduction, and you do all of this in parallel. You have capital H of those transformations in parallel, and so you can just concatenate the result at the end and add 1 more linear operation. This is a complete description of transformers. Okay, this slide. I hope it was clear, and if it wasn't, please ask questions, and I will be happy to answer them at the end. Okay. Now, once you have processed, a sequence of tokens, a set of tokens, now you can do various classification tasks on the final token representation. Okay. So let's talk about one application of transformers, which is natural language processing, which is a key, one of the key applications that was really transformed by transformer. So in natural language processing, each token xi, it represents a word together with its position. So imagine you have a sentence and you want to process this sentence with a transformer. So a sentence is nothing but a set of words together with their position. Okay, it's not just a bag of words, but the words also come with their position. Now, the first thing that you need to do if you want to apply transformers is that you need to embed both the word and the position in high-dimensional space. So this is the role of the tokenizer and the positional encoding, which we won't talk about, but it's simply, intuitively, it just tells you how to transform a word like cat and a position like 7 into vectors in dimension d, which could be, 1,000 or 10,000, okay? So this is the role of the tokenizer and the positional encoding. Now, once you have done that, now you can start to train transformers on many, many different tasks. A basic one would be translation, for example. You have an encoding of a sentence in English, and you want to train a transformer so that it gets you an encoding of a sentence in French. Okay, that's one possible objective. Now, there are many other objectives. Now, let me tell you about some famous transformer models that have been trained over the last 5 years. Okay, so one thing that I want to clarify is that it's not that easy to train those transformers, especially when they become large. That's the reason why some of them become famous, because those transformers which are hard to train, they become useful for lots of fine-tuning tasks. So once you have trained them, then they can become like machines that you can fine-tune on tasks of specific interest. Okay. I also want to make a comment about references in this talk. So transformers was introduced in 2017, 5 years ago, in a paper by Vaswani et al. At Google. And in general, I'm going to have very, very few references in this presentation. There are many reasons for why I don't have time to give references. But certainly, please go look at the Lego paper. In the Lego paper, we have a related section, which is well done, where we explain, all the references, all the relation to prior work. So please, take a look at this. And I'm sorry that I'm not giving more references during the presentation. All right, so let's go through some of those famous transformer models. So to me, one of the most important one is BERT. So what is BERT? So BERT is an encoder-only architecture. It doesn't matter what is encoder and encoder-decoder. I just explained to you encoder-only. Encoder-decoder is a little bit different, but it's not going to matter for this presentation. So BERT is an architecture which was trained on masked language modeling. So what does it mean, masked language modeling? It means you have a sentence, let's say in English, and you're going to mask like 10% of the words. And your task is going to be to uncover what were those masked words. Okay, so that's a very simple task. But you can imagine that you really need to understand language if you want to solve it. Now, what are the parameters of this BERT model? Capital D is going to be the depth, the number of layers. So it has 12 layers. Capital H is the number of heads. It has 12 heads. Okay, so 12 layers, 12 heads. Each word and position is embedded in dimension 768. Okay, so almost 1,000-dimensional space. Now, in total, if you do the calculation, and you have understood what I explained on the previous slide, this amounts to a total number of parameters, little p, of 110 million. Okay, so 110 million parameters for BERT, and roughly the way it's divided is 1/4 of those parameters, they go in the multi-head self-attention, 1/4 goes at the very beginning in the embedding, half of them are in the feed-forward neural network, which are at every layer. Okay, so you understand there are 12 of those feed-forward neural network, one per layer. Okay, so that's BERT. Another one, of course, that everybody has heard of is GPT, GPT-2, GPT-3. So GPT is nothing but a transformer, in fact, a decoder-only architecture, but again, this is not very important for this talk. And it has been trained on the task of predicting the next word. Now, people over the last 5 years have done a lot of research, on variants of, transformers. One of them that I like that we're going to talk about today is Albert, which is exactly like BERT, except that it's the same layer being repeated over and over again. Okay, and from a theory perspective, it's really very appealing, to just repeat the same operation and again and again and again. Okay, this makes a lot of sense. It has a lot less flexibility than something like BERT, but maybe it has a better inductive bias, which is something that we'll come back to. Now, another direction, in which people have done research is training better those models. I have not explained how you train them. Of course, you train them with stochastic gradient descent, but there are lots of details. What is the momentum? What is the learning rate? What is the mini batch, etc. And Roberta, for example, is an example where they took the BERT architecture and they showed that you can train it much better, in fact, and get much better performance. Okay, so this is Roberta. Another one that I want to mention is DeBerta, where basically in DeBerta, you have this attention, and you remember I told you that you need to embed both a word and the position of the word, but you could have an attention that tries to disentangle attention with respect to position and attention with respect to words. And this is exactly what the DeBerta does. So, you can play with the attention module and try to have attention focus on different things. Okay. Now, all of these are applications in NLP, but transformers have transformed, the field of machine learning way beyond natural language processing. So transformers are used even for reinforcement learning, okay, for decision making. They are used in vision, these VITs, vision transformers. They are used in physics applications with graph transformers. They are used for multimodal application where you try to mix in, text and images like Clip and DALL-E. So, DALL-E, it's basically translating a sentence in English into an image, okay? So lots and lots of application. Now, this is all great, and, I love, ML application. But at this point, maybe you might be wondering, why am I, talking about transformers? Like, if you followed my work, you know that I like to prove theorems. I like to understand things theoretically, like the law of robustness, convex optimization, etc. Why is it that I'm, getting into this business of actual, transformer, very large neural networks, and their gritty details? So the reason is that the results that they are obtaining are actually completely crazy. They are really, really, really impressive. So I will just quickly go over this image. So many of you have seen this headline from a couple of months ago. A Google engineer who thinks the company's AI has come to life. So this was one of those large language models, Lambda, it doesn't matter the name. And this Google engineer was interacting with the AI, and the AI was just giving responses that were so convincing that this guy thought that, okay, it has become sentient actually, and it's a real, it's an alive thing. So of course, that's nonsense. It's not the case. But the point is, the AI was just so good that it was able to fool this person. Okay, so this was not possible just a couple of years ago. This image is an image from DALL-E, where the prompt was a still of Kermit the Frog in Star Wars 1977. And you see, so Kermit the Frog is whatever, this puppet frog, and it's able to dress the frog in, Yoda's clothes. So that's really amazing, because it needs to understand, like what are body parts, for example. It has understood, very abstract concept. Now, of course, I'm not the one who put in this prompt, so you might be saying, oh yeah, maybe, this was, handpicked, and, like a typical answer will not be as good. So this is the prompt that I gave myself. I worked in the past on the multi-arm Bandit for a long time. And for a long time, I wanted to have a picture, that I would put on my blog, which would be a picture representing a bandit writing mathematical equation on the blackboard. So I just asked, I was too lazy to ask an artist for many years, but now I can just ask DALL-E. And this is the image that he produced. Okay, so I think that's really impressive. Again, it needs to understand that the chalk goes into the hand, that the chalk goes on the blackboard. I mean, it really understands lots of things. Okay, so this is why I think we should really spend a significant effort now to try to understand those machines, and this is really part of the future. Okay, so let me tell you what is good about transformers from my perspective. What's good to me is that transformers, they are really relative machines instead of absolute machines. Here is what I mean. If you look at convolutional neural network, they test their input, X, an image, against a bank of filters that it has learned. Like, for example, maybe there is a filter for cats, there is a filter for dogs, there is a filter for a table, etc. So it tests, against this bank of filters that it has learned. Now, what transformers do is that instead of testing against a fixed set of filters, it tests part of the input against another part of the input. And testing one part of the input against another part of the input, this is what enables to do reasoning, to have analogies. You can start to associate concepts. You can say, oh, I know that concept A behaves in such and such ways, and now I have concept B, and the transformer is going to compare concept B to concept A, and is going to be able to make some induction based on their similarities. Okay, and this is really the essence of reasoning for me, and I think that's why those architectures are so successful. Now, of course, this paragraph, this sentence, okay, it's a nice sentence, but it's very non-scientific. Can we try to put this on more solid ground? Okay, so, and this is what I'm going to try to talk about today. This is where Lego enters. So Lego is this synthetic task that I'm going to tell you about, which we're going to use to try to understand how do transformers do reasoning. Okay, this is going to be our goal. And then, maybe if we understand how they do reasoning, maybe we can also improve them a little bit. Because at the end of the day, we don't want to just understand for the sake of understanding. We want to understand so that we can have an impact on the way the field is evolving. Okay. So at this point, the plan is to switch to Lego, to tell you what is this synthetic task, and then to show you, experiments that you can run with transformers on Lego and some of the insights that you can get from it. Okay, so this is the plan for the next half hour. All right, so let's go into it. So Lego stands for Learning, Equality, and Group Operations. Okay, and I will introduce it at a slightly abstract level, but we'll get very, very concrete in just a second. So at an abstract and high level, here is what's happening. We're going to have three sets that define the task. The first set is capital G, which is a group acting on a set of values, capital X. Okay, so we have a group. So if you remember, from your first year of math studies, a group is, for example, a group of permutation, or many other group, maybe a group of rotation. You're rotating some object. Okay, so this is going to be my group of. If you want, capital G is a set of operations that we're going to allow on a set of values, capital X. For the set of values, you can think, maybe you have an object that you're rotating, or more simply, maybe capital X is a set of numbers, something simple. Now, in addition to those two sets, you have also capital A, which is a finite alphabet, and capital A is going to be a set of variables. Okay, so you have those three sets. Now, Lego is going to be, sentences like in natural language, but it's not natural language. And a sentence in Lego is going to be made of a bunch of clauses. And what is going to be a clause? A clause is going to be of the form A equals GX. So what this means is that it's a clause, you're going to have a bunch of clauses, and each clause is going to give you a relationship between a variable A. So little a is going to be in the set capital A, and it's going to tell you what should be this variable little a. And it's going to tell you that it's a group operation G applied to little x. And little x is going to be either a value or a variable itself. So if it's a value, then the meaning is clear. If little x is a value, then G applied to x is just, the group operation on x, which is another value, and you should assign to the variable a this value. Now, if little x is itself a variable, then I'm giving you, a relationship between two variables. So you're not able to know what are the values yet. You just know that, little a is the transformation little g applied to the variable little x. But you don't know what is the variable little x. But maybe there is another clause that's going to define for you what is the value of little x. And this is going to be the point. Lego is going to be a bunch of those clauses, randomly, arranged, but it's going to represent, in fact, a chain of reasoning, where at some point you're going to start with some fixed value, and then you're going to have an edge, which is a group operation, telling you what is the next variable going to be. So the next variable, so A equals GX, I view it as an edge in a chain of reasoning, and you're going to have a simple chain of reasoning. Now, what is going to be the goal? The goal is, given such a sentence, you would like to resolve the value of each variable. You just want to find the assignment, the value in capital X, that you should give to every element in capital A that appear, so that all the clauses are satisfied. That's what you want to do. You just want to resolve, this system of equations. And for this presentation, we're going to focus on the simplest possible case, but I wanted to introduce a general one just so that you see that it's much more powerful and more general, and there is a lot more you can do. What we're going to do is we're going to focus on the simplest case of the group on two elements. So capital G is just multiplying by minus or multiplying by plus. And the set of values is just going to be -1 and +1. And capital A is going to be the Latin alphabet. So just to be clear, here is what a Lego sentence going to look like for the next half hour. So a Lego sentence is just going to look like maybe variable A is equal to +1. So that means it's a group operation plus applied to the value 1. So little a is equal to 1. Now B is equal to -a. Okay, great. So B is equal to -1. C is equal to +d. So this is like slightly more complicated, because if I'm processing from left to right, when I get to C equals +d, I don't know what is d. Okay, so I have to kind of keep it in memory. Now let's go to d equals +b. I knew that b was equal to -1 through this clause. So now I know that d is equal to -1. So now I know that c is equal to -1. So you see, I need to follow this chain of reasoning to keep track of the operation that I have already done, so that I can keep, filling in the variables one by one. Okay, so this Lego sentence results into ABCD equals 1 -1 -1 -1. All right, so I hope this is clear. Now what we're going to do is that we're going to, generate a large-scale training set of Lego sentences, and we're going to train a transformer on it, a BERT transformer. So again, just to make sure that we're on the same page, you see you have this transformer, and the input is maybe D equals C, B equals blah, 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 A equals +1. Now, each of those are tokens. Now, the transformer is going to process this set of tokens, and it's going to produce a high-dimensional embedding at the end of the processing. And what we're going to do is that we're just going to add a linear classification head on the variable at the end of the processing, so that we have to predict, is it a +1 or a -1? And we get, an objective function that evaluates us on whether we have solved the problem correctly or not. Now, the key point, what I want you to understand, why did we introduce Lego? What's the point of Lego? The point of Lego is that you need to be able to do two very basic operations of reasoning. One is to associate concepts. If I tell you A equals +1, blah, 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 Z equals -A, you need to understand that these two occurrences of A they are the same thing. They should be related to each other. And associating concept, this is really at the basis of reasoning. Arguably, it's at the basis of mathematics. To group things which looks different into a same thing. This is like one of the points of abstraction. All right. So associating concept is something very fundamental, and it's very important to solve Lego. The other thing that you need to be able to do is to manipulate locally those concepts. For example, if I tell you that some variable x is 1, but now I tell you a is equal to minus x, then you need to take this 1 and to apply the group operation minus to turn the 1 into a minus 1. Okay, so you need not only to associate things, but you also need to be able to manipulate them, all the while following the chain of reasoning. Okay, so this is how you can solve Lego. Now, the point, about transformers for Lego is that these two operations of association and manipulation, you can very easily do them with attention. So let me explain that to you. How do you do, association and manipulation with attention? So let's start with association. Let's say you have two occurrences of the variable z in your Lego sentence. And right now, I've already processed this token z. Maybe it was embedded at the very beginning at the input into alpha. Alpha is a vector in Rd. And now I have processed these two tokens alpha, with their position. I have processed them, through the transformer, and maybe I'm at layer 7. Okay. Now, maybe at layer 7, the first occurrence of z is embedded in alpha plus beta, and the second occurrence of z is embedded into alpha plus gamma. And let's say that no other tokens contain alpha because the variable z only appeared twice, and all the other ones, they don't contain alpha. Now the key thing to understand is that the inner product between alpha plus beta and alpha plus gamma, let's say all those things are normalized to be unit norm. The inner product between alpha plus beta and alpha plus gamma, this is of order 1 because you have an alpha inner product with alpha. But if you take alpha inner product with some other random token, then by high dimensional concentration, this is going to be much smaller. This is going to be 1 of order 1 over square root of the dimension. So what I'm telling you is that the inner product between alpha plus beta and alpha plus gamma is of order 1, but the inner product of alpha plus beta and any other token is going to be very tiny, of order little o of 1. So if you have an attention head whose linear transformations are the identity, you're really literally comparing tokens with each other, then the first occurrence of z is going to attend mostly to the second occurrence of z. You see, they are going to look at each other, and they are going to transfer, like what the attention head is going to do is that it's going to transfer information from one occurrence of z to the other occurrence of z. Namely, after an identity attention head, alpha plus beta becomes alpha plus beta plus alpha plus gamma. So you have transferred the gamma information into the tokens that are beta. So that's how you do association. For manipulation, remember that you have positional encoding. So you know what is the position of the different tokens. So using this positional encoding, what you can do is that you can mix in, you can do a local convolution, and you can mix in some of the tokens. So let's say I say, A equals minus, B. Then I can put in A, I can put the minus token, and I can put the B token. This I can do. And now the feed-forward neural network can do the operation for me. If it sees that in A, I have maybe the minus group operation and I have the +1 value, then the feed-forward can turn this into a -1 token. Okay, so you can do the manipulation by a combination of the attention and the feed-forward neural network. Okay, good. So this was maybe slightly abstract, of how, in principle, transformers could solve Lego. But let's run actual experiment and see what's going on. So again, what is a Lego sentence? A Lego sentence is A equals +1, B equals -A, E equals +B, etc., and so on and so forth. So this corresponds, you should think of it as a chain of reasoning like this. I have the node A, and I know it's related to the node 1 through a plus edge. I have the node B, it's related to the node A through a minus edge, and so on and so forth. And note that you have the order in which the variables appear in the Lego sentence, which is different from the order in which the variables appear in the chain of reasoning. Now I'm going to call variable A is going to be the first variable because it appears first not in the sentence, but because it appears first in the chain of reasoning. Okay, so I'm going to order my variables, and we're going to run transformers on Lego sentences with 12 variables. Okay, And we're going to look at a lot of plots like this. So here is what's going on. So this is a randomly initialized BERT that we're going to train on Lego sentences. On the x-axis, you see the number of epochs. On the y-axis, you see the testing accuracy. Each line corresponds to different variables, variable 0, 1, etc., and so on and so forth. And you see what happens is that everything shoots up to 100% accuracy. All right. And note this is test time accuracy. So, I have a training set, and then at test time, I draw a new Lego sentence, and I ask you, can you complete it? Okay. So it's amazing. Transformers can solve Lego. They do very, very well. And you see, first it learns to fill in the first variable, then it learns to fill in the second variable, then it learns to fill in the third variable, and so on and so forth. Okay. So it learns the variable, in the order of their chain. That seems to be to make complete sense. Okay. So do we go home? Transformers just solve Legos. There's nothing else to be said. So of course not. What we have to do now is to think this through a little bit, because we're testing on the same distribution as the one that was trained on. Okay, so this is classical statistical learning generalization. But here we're asking for a little bit more. We would like to know whether the transformers really understood the logic of solving a Lego sentence. And one way to test that would be, for example, to change a little bit the distribution at test time. What is one natural way to change the distribution at test time is to maybe add more variables. Maybe you were trained to solve Lego sentences with 12 variables. What about if I ask you a Lego sentence with 24 variables at test time? Okay, so that's what we're going to do. Now you need to be a little bit careful, because you need to account for the fact that there is positional encoding. And you want to make sure that at training time, the transformer has seen all the position. Otherwise, it's going to be too hard. So the way we're going to do that is that we're only going to ask Lego sentences with 12 variables, both at training and test time, so that it has always seen all the position. But at training time, we're only going to provide supervision on the first half of the variables. Okay. So for example, here, I'm only providing supervision on the blue nodes, and I'm not providing supervision on the pink nodes. But at test time, I'm going to evaluate you on all the nodes. Okay. Now, here is what happens. What happens is that it doesn't work at all. Okay. So transformers do not generalize out of distribution for Lego. So you can see the dashed lines are the variables 6, 7, etc., which are those that did not appear, that for which supervision was not provided at training time. Okay. So even though in distribution it works great, it doesn't work at all out of distribution. Okay. So let's see. So this is a real problem, and we need to think about how can we fix it. First of all, it shows to you that transformers are they're not this universal and final machine that is going to solve everything. Like here, you can really directly see that it has some deficiencies. It's not able to extrapolate to longer lengths. So can we fix this? And maybe, can we go back to the basics of learning theory and maybe have a better inductive bias to fix this? And this is where I'm going to come back to this idea of Albert. You remember? So Albert is like BERT, except it's the same layer which is repeated again and again, and meaning that the weights of every layer is tied together. And maybe this is more appropriate for Lego, because Lego, one simple way to solve a Lego sentence is really to do a for loop. Okay, so this for loop, Albert immediately implements it. So maybe it will generalize better. So let's see what happens. So I'm on the top part. You see, if you do training and testing in distribution. Okay, so here the top plot is when I train, providing supervision on all 12 variables, and you see both BERT and Albert do great. Now on the bottom, I show you again this out of distribution, where you train by providing supervision only on the first half of the sentence, and you're really asking, okay, can you complete everything? And you see that Albert does much better out of distribution. You see that BERT, it struggles to get even 70% accuracy on just one more variable, but Albert, it gets 100% accuracy on one more variable. It gets 100% accuracy on two more variables, 7, and it gets to 70% accuracy on 3 more variables. So it really, is able to generalize, to extrapolate in terms of length much better than BERT. So, inductive bias is still a real thing, and it really matters, and you should still think about inductive bias for your application, even if you're using this very powerful transformer system. Now, good. And note also that Albert is smaller, right? It has only 30 million parameters compared to BERT. So maybe you're asking, you could be asking, oh, maybe it's because it has fewer parameters that it overfits less. But you can train a BERT model with 30 million parameters and it's not going to work at all. Okay, so now I want to just do a small aside on something, a phenomenon which I find really interesting. So let's look at the upper right picture. And let's look at the order. So this is randomly initialized Albert, trained on all 12 variables. And let's see what happens, in terms of the order in which the variables are learned. So you see variable 0, the first variable, it shoots up to 100% accuracy first. Then it's variable 1 that shoots up to 100% accuracy. And look at what is the third variable that shoots up. It's the last one. It's variable 11. So how is that possible that, you get high accuracy on the last variable before you get high accuracy on any variable in between? What is going on there? So why does the last variable accuracy improves before all the other one, except the first and second one? Okay. Well, it's because there is a shortcut in our task. The last variable, you can predict it just by taking the product of the minuses. You can just count how many minuses appear, and you take the parity, of the number of minuses, and this will give you exactly what is, the correct classification, the correct label for the last variable. Now, this intuitively, if you do this parity trick to get the value of the last variable, this should be really, really bad for generalization, for out of distribution, for length extrapolation. Okay? But if you look at the plot carefully, we didn't see it in the plot that, generalization was very bad. And it's because in our setup, the last variable, it's not really the last variable in the chain at inference time, because we only provide supervision on the first half. So let's do a different, experiment where we also add supervision on the very last variable, and let's see what happens. Okay. So here, what I'm doing now is that I'm showing to you what happens. So on the top plot is I add supervision on the very last variable, and on the bottom plot, it's the same first 5 variables, but just not the last one. And you see, by adding more information, I'm adding supervision on the last variable, suddenly the performance is worse. Okay. So adding more information does not necessarily improve, because sometimes adding more information can lead to shortcut solutions which do not generalize well. Okay. And here's a key point to understand is that classical generalization is really misleading. Okay. Not only did it not indicate whether you length extrapolate, but also it can change, the type of solutions that you're going to find. So not only do you need to think very carefully about your inductive bias, what type of architecture tricks are you going to use inside the transformer, but you also need to think very carefully about the objective function. Okay, so now I want to go back to the inductive bias. So let's try to keep improving, So I already showed to you that Albert improves on BERT, but can we do more tricks? So another trick that we can do is realize that for Lego, the first variables in the sentence, you should be able to resolve them much earlier inside the network. So what we're going to try now is this idea of stochastic depth, where we randomly stop the network at a random depth. And if we randomly stop at a random depth, then it should incentivize the network to solve the variable as quickly as possible, because it doesn't know when it's going to be stopped. So it really should keep incentivizing the network to really do this, common sense solution of solving variables one by one. So let's see what happens. So on the left, this was the randomly initialized Albert that I told you about, and it works great. And now here's what happens if you add stochastic depth. It works even much better. Now it does, extrapolation 100% accuracy to +3 variables, and it's starting to get, to +4 variables. Okay, so you can see that we're really going in the right direction to actually solve the Lego problem by adding the right inductive biases. Okay, good. So we already got a few insights from this Lego thing, but now I think, if there are real deep learner in the audience, you're probably screaming out of your lungs that I'm doing this wrong, and meaning that really in deep learning, you should never train a network from scratch on a task of interest. What you should do is you should pre-train on a huge data set so that, some good learning happens, and then fine-tune on the task of interest. Now, of course, you could do that here, and maybe you could, pre-trained BERT. You could use the pre-trained BERT, which was pre-trained on Wikipedia, for example, and you can try to fine-tune it on Lego. But, from my perspective, it would be like, why the hell would, pre-training on Wikipedia help in any way to solve Lego? It's not like you're going to read Wikipedia and somehow learn to reason, and then you can learn Lego. This doesn't make sense to me, okay? But let's try it. Let's see what happens. And lo and behold, it works amazing. So on the left is a randomly initialized BERT, which does not do lens extrapolation almost at all. And on the right is if we take the pre-trained BERT and fine-tune it on Lego. And look at that, it works amazing. First of all, it shoots up in accuracy way before the randomly initialized BERT, but also it does lens extrapolation very well, and it keeps climbing up. Okay, so what's going on there? I mean, is this magic? So should we just stop and praise the deep learning gods that pre-training is this magical thing? So of course not. We're going to try to understand what's going on. And what we're going to do is that we're going to be very pedestrian and just look at the attention head, just plot them, in your Jupyter notebook and see what they look like, those attention heads. And here are two attention heads that were carefully, selected. And, I don't really have time to explain in detail what's going on, but basically on the left, what you see is exactly a manipulation head. You remember I told you that you need to mix in locally the tokens if you want to, resolve each clause independently. And this head on the first layers, head number 3 on the first layer, is exactly doing this manipulation. Now, remember I also told you need to do association. Well, this head on layer 1, head 11, is exactly doing the association. You see like this red dot here, they are really associating 1A in one clause to 1A in another clause. Okay, so maybe these are the manipulation and association head, and these heads are there at the end of pre-training. So maybe this is a reason why pre-training is so successful, is that manipulation and association are just generally good concepts. And when you were trying to do mass language modeling on Wikipedia, somehow the transformer has learned this operation. And now when you fine-tune on Lego, you start with this good operation. So of course, you're going to do much better. But this is an hypothesis that we can test. Okay, we can simply, let's try it, instead of pre-trained BERT, let's do a randomly initialized BERT, but where at initialization, we fix 2 heads in every layer, which are doing this association and manipulation. And let's see whether it can reproduce, the benefits of pre-training. And it exactly does. Okay, so again, on the left is a randomly initialized BERT. On the middle is a pre-trained BERT, which is doing much better. And on the right is mimicking BERT, which is, you understand, mimicking BERT has seen nothing of Wikipedia, no pre-training at all. It's randomly initialized. Just we're careful, and one of the head is doing association and one of the head is doing manipulation, and it basically mimics the behavior of pre-trained BERT. Okay, so I think it's at this point it's natural to ask whether this is a more general phenomenon, and maybe pre-training in general finds this this useful general purpose operators, and then these general useful these general purpose operators, they can be fine-tuned for task-specific operation. I think that's probably what's going on. Okay, so let me now finish with just one more idea, and then go to the conclusion. So one more idea is that the manipulation head is really like a small filter convolution. So what about embedding this convolution directly inside the transformer? So one thing you can do, and it was proposed by other people, is to replace the linear operation that you use to build the key, query, and value by convolutional operator. And this is what you will get. This works really great. So convolutional BERT and convolutional Albert. Again, on the top is just classical in distribution, and on the bottom is this lens extrapolation. And you see that even convolutional BERT does really well at lens extrapolation, much better than before if you add this convolution. Now we can try to take the first step of bridging the gap between Lego and reality by taking inspiration from the fact that Lego really looks like some very basic code. Okay, so we consider the problem of executing C code. So you have C code that looks like this, and your task is to apply a transformer to it so that it really executes the code directly. And what we did is we just compared, vanilla pre-trained BERT fine-tuned on this task of executing code compared to our convolutional BERT. And you can see we get for free a 2% improvement in test accuracy, which, is pretty rare in deep learning, that you would get 2% by just doing this tiny, add-on. And here we really get it, because these convolutional ideas are just a good idea. And a lot more, remains to be done and explored in that space. Okay, so let me move to the conclusion and then take some questions. So maybe the most important conclusion of all is that those large language models, the community is slightly, maybe a little bit giving up on trying to understand them, but I think it's a bit too early to give up. And maybe we can really understand, what they are doing, and, so the association and manipulation head, that's one part of what they are doing, but there are many, many other type of basic operators that we could find. Another thing that we saw is that classical in-distribution generalization can be very misleading, and architecture, like in distribution, transformers work great off the shelf. But if you want really this extrapolation properties, this, out of distribution generalization, then you need to bring back, the inductive bias. So we saw Albert with weight tying, stochastic depth, convolution, etc. Now, of course, at this point, we don't have really result on improving state of the art on some real benchmark. Maybe we can try to use some of the insights that were discovered with Lego to do that. That would be fantastic. And a lot more remain to be understood, such as the importance of depth, dimension, the exact role of the feed forward, what happens when you have more complex group, etc. And, we have many, many more findings. So I will just give you some of them. So in the summer, we kept training more transformers for Lego. For example, Lee was able to train a BERT model that can solve Lego up to length 100. So like 100 variables, which is really crazy and completely different from what was done in this presentation. It cannot do just the for loop. It's doing something completely different. We also found that layer dropout is a great way to give length extrapolation. Tian Lekai from Princeton studied efficient transformers, and we have some insight for why, efficient transformers are not working. Ruo Chichen, who was an intern from UW, she trained transformers for Lego when you don't have a finite number of variables named, but infinitely many variable names. And this has very deep relation to executing codes, which I don't have time to talk about. But maybe this is a good point for me to stop and see, if there is any question in the audience. Thank you very much.
Yeah. Hi, all again. Actually, I hope you enjoyed. And now, actually, we come to Q&A session as you're expecting. So most are voted. We started with a question from Dmitro. How to fine-tune a transformer efficiently? Are there any peculiarities compared to CNN and FCNs?
Yes. Yeah, absolutely. So great question. So there is a ton of work on fine-tuning transformers, and this is an excellent question. In fact, we haven't done this work of trying to see how the different fine-tuning methods they work on Lego, and it's a good question. I now wonder about it. I can tell you some of the ideas for fine-tuning transformers. For example, people have done these adapters where you just add, one feed forward in every layer, and you only fine-tune this feed forward. Okay. Another thing that people have done is LoRa, which is called low rank adaptation. So what LoRa does is the following. So you have a matrix, okay, which corresponds to, let's say, the first layer in your feed-forward neural network, and let's say it has d-squared parameter. You could try to fine-tune all d-squared parameter, but instead what we're going to do is that we're only going to add a low-rank perturbation to this matrix, and we're only going to fine-tune this low-rank perturbation. And this turns out to work really, really well. And, we have no idea theoretically why it is the case, but this is one example, where it's a very transformer specific fine-tuning technique, and it works great in practice.
Okay, sounds great, Dmitro. I hope you're satisfied with a couple of ideas. And let's go next. Okay, Bogdan Pitaychuk. I hope this was correct. Is there any research on persons of useful tokens in big LM, and which heads are mostly being referred to, or with which can be dropped without a loss of accuracy.
Okay, excellent question. So the two questions are good. So let me answer the second question first. So this pruning question that you're asking, I mean, this is in my conclusion slide, I went over it a little bit quickly, but pruning is of course one of the things that you might want to do, after the Lego research. Why is that? Well, the Lego research kind of shows to you that, for example, for Lego, really what's important is to develop those association and manipulation heads. So what you could imagine is at pre-training, you have all those heads that are kind of doing an exploration, a sort of lottery ticket hypothesis. And some of them are going to be lucky and develop into association and manipulation. But now you can drop all the other ones. So at the fine-tuning stage, I think it makes a lot of sense to explore more the pruning techniques where maybe you want to drop some of the heads. Right now, we don't really know how to do it, but I think it's a great direction. For the first question, what is the percentage of useful tokens in big language model? So, this is still a dark, magic, dark art. So we don't know, how to build the best possible data set for, let's say for transformer learning. I think what you're getting at is maybe, for example, if there are lots of repetition, maybe that's not great. And maybe you would like to remove repetition from your training set. Maybe this will lead to use less tokens. But we really don't know how to answer this question at this point.
But maybe we tried. Okay, Helena actually asked, how is Lego improve transformers? How its influence on, let's say, NLP tasks? Is learning become faster or more accurate?
Yeah, so I think it's a little bit early to ask for, whether it has influenced the field in any way. It hasn't, this is a very recent research. But I can tell you that for me personally, I feel like I understand transformers so much better after doing this project. Like I really have so many more insight into what's going on. And more than insight, I also don't feel anymore that it's a completely hopeless black box. Like, we were really able to open the black box and see all the different parts, acting together to solve the task. Now, maybe, concretely at the end, I talked a little bit about, the problem of code execution. And this is somewhere where, you really want to do this association and manipulation. And I think maybe at a more high level, I think it's pointing you towards a direction where we might want to change the initialization of transformers. And by that, I mean, right now, everything is initialized randomly. But maybe we want to initialize with some diversity of heads. Maybe, one head should be initialized with a Fourier transform matrix. One head should be initialized with an association, matrix, and so on and so forth. So I think it's pointing you in this direction, which, we are currently exploring, but it's a very vast, playground. And I don't know which direction is going to be the most successful.
Yeah, maybe people actually will choose. Okay, the next one, Helena. Is there opportunities to use Lego with happy transformers?
So I don't know what is happy transformers. If you can.
As I understood, it's the library, Python library built on top on happy faces.
Oh, I see.
Hugging face. Oh my god.
Okay. Very good. So, I don't know if this will answer your question satisfyingly, but we have a GitHub repository for Lego where all the code is there, and I think you can start there.
Not long. Okay. Dimas and Joke. Yeah, we expected maybe there's some drama.
Yeah,
Why they are called transformers?
So I don't know, I wasn't there in 2017 at Google when they came up with it. So I really don't know. In the papers, they don't really explain it. In fact, there is still for me lots of mysteries around how they came up with this architecture. I don't think it's the final architecture in any way, yet it works so well. It's really a mystery. I don't know why it's called like that.
Yeah, maybe you can find dramatic answers on the Quora, so people will investigate it. Okay, let's go next. Bogdan Pitaychuk, please. asking in computer vision, for example, the quantized approach in vector quantized via and vector quantized GAN,
Yes.
etc., showed good results. Is there any work trying to apply head convolutions codebook into transformers?
So there are lots of papers trying to do, trying to put convolutions in various parts of the transformer. And I in the Lego paper, you can see in the related related work section, we reference a lot of them. As far as I know, at the moment, none of those methods really shows a significant edge. So it's always the case that if you just apply, the basic transformer architecture, but just a little bit bigger, then you recover any advantage that was done through, various tricks like this. So there are works, but it's not yet successful, I would say.
People are trying.
Yeah.
So we just need time. Maybe we will get the right solution. So again, Dima Samchuk, could you please elaborate on the question, what is embedding parameters?
Mm-hmm. Yes, absolutely.
Is understand attention, embedding parameters.
Yeah, embedding parameters is extremely simple. So you have the English vocabulary. This is just a finite set, whatever. Let's say it's of, I think it's 100,000, words or something like that. Now, for each of those words, each word independently, you're going to find a high-dimensional vector. What does it mean, find a high-dimensional vector? Let's say at initialization, it's just going to be a matrix where number of rows is the vocabulary size, and number of columns is the dimension of the embedding, and you're just going to fill in this table at random. Okay, this is going to be your embedding. Now, if I see the word cat, I just go to the row corresponding to cat, and the high dimensional embedding is this row in this table. Okay, and the point is, we're also going to do gradient descent over this table. Okay, so we're also going to update the embedding parameters.
I feel it's really great explanation. Mitra, I hope you're satisfied, or maybe you still have time. Ask one more question. Okay, and Yusuf asking, will transformers take over AI? Yeah, it's intriguing.
I think it has happened already,
Already?
Maybe this question was a question, 2 years ago, but I think now, I wouldn't say the jury is still out. Like, I think Transformers is just completely taking over AI, absolutely. Maybe your question is whether it will remain like that. And that, of course, nobody knows, but I think there is a chance that a transformer-like architecture, again, remember my slide where I was telling you that transformers are these relative machines compared to more absolute machine like convolutional neural networks. I think this is just a good idea to be relative rather than absolute. So I imagine this will stay. Now, whether exactly this architecture will remain, I don't believe that will be the case, but something like that, yes.
It's yes. That's definitely yes. So we're in a new epoch. Just stepped in. Okay. It seems like we getting to finish now. Actually, our meeting. So, guys, I hope you enjoyed. But I must also give a couple of notes. We will have the new talk next week from Alexander Rush, the associate professor at Cornell Tech and researcher at Hugging Face, just mentioned a couple of times ago. He will share the knowledge on prompting, metadata sets, and zero-shot NLP. So please join us. You get really interesting stuff, and also I will be really happy if you help us a bit in a moment on Slido and answer one more question. Just how do you like the session today? This is small poll. Answer is really quick. Please help us, and I hope I'll see you next week. Check your inbox for dates, please. Bye-bye.
Thank you, everyone. Bye.